this video we're going to look at a few derivations for equations that we use when we're looking at light. The first derivation we're going to look at is the relationship between the angle of the maximum and the wavelength of light. So first off, let's draw a diagram of our setup where we've got two light sources, a screen, an angle that's defined by the central point between the slits and the angle of the first maximum. We also have the distance between the slits here. Now the path difference at this arbitrary point is this S2 to D, which will be a multiple of the wavelength used. Now looking at this triangle here that's created from D to S1 to S2, that angle there is theta, matching this angle that's created here, because the angle between two lines is equal to the angle between their normals. Now looking at the larger triangle from S1 to P to D, if we consider the distance to the screen to be 30 centimeters or more, and the distance between the slits being extremely small, this angle here is around about 0. And if that's the case, that means that this angle here, PS1D, and also PDS1 are both around about 90 degrees. And what that means is that the triangle S1DS2 is 90 degrees at that angle. Because that triangle is 90 degrees, we can use our trigonometry, and we're going to find the relationship between the angle, this opposite side which is a multiple of the wavelength, and the distance between the slits. We're going to use the sine rule, so the opposite over hypotenuse, and we receive this relationship here. And then rearranging this equation, we can find the path difference is equal to the distance between the slits times the angle of that first order maximum. So previously where we had delta S in this equation, now we're going to say it's m lambda being a multiple of a wavelength. And that's when we receive our maximum, where m is either the first, the second or third order maximum and so on. If we're looking for the minimum, we can still use the same equation. However, we replace the m with m plus a half, representing the situation where we get destructive interference. So this is always a popular question in exams. Have a look through this video again to make sure that you can do it, and also see if you can find this formula on the formula sheet. Now we look at another derivation, which looks at the relationship between the distance between the slits and the distance between adjacent maximum in the interference pattern. So in this case, L is the distance from the slits to the screen, delta Y is the distance between the central maximum and the adjacent maximum, and the path difference from S1 and S2 to this point here is given by the equation we just derived. Now as this angle theta here is very small, so we're looking at that great distance from the slits to the screen and the small distance between the maximum here, the angle is small, and at small angles sine theta is roughly equal to tan theta. So this is an important assumption that we make. Now the reason why we assume tan theta is because when we're looking at this triangle, P0, M, P2, this big triangle here, we want to know the opposite and adjacent. So the opposite of this angle is that delta Y, the adjacent is the distance from the slits to the screen. Therefore, our previous equation of d sine theta is the wavelength, becomes d tan theta equals the wavelength. Now substituting in the opposite and adjacent into this equation and rearranging, we can find the relationship between the distance between the maximum, the wavelength, the distance to the screen, and the separation between the slits. The third derivation we'll look at is that of the pattern produced when we've got a diffraction grating. So a diffraction grating is now multiple slits in small space. Now one of the tricks with diffraction grating is to determine the correct value of the slit separation between two adjacent slits. So if you've got multiple lines per meter or per centimeter, careful with the calculations, but the slit separation is given by D equals 1 over the number of slits per meter. If light is diffracted from slits A and B, theta is the angle that is made with the normal, and theta is also the angle here due to the previous rules that we've had. The path difference is given by d sine theta, just using laws of trigonometry. Now at a point on the screen where constructive interference occurs, the path difference must be an integer multiple of the wavelength, being m lambda. So therefore, d sine theta is m lambda. And notice that this is the exact same equation as for double slit. Adding to that, sine theta has a maximum value of 1. So when we use this equation, there's a maximum number of spectra that we can observe on the screen.